So another important parameters to determine in determining the quantitative index for plant is the cover. So cover is the vertical projection of vegetation from the ground as viewed from the above. So two types are recognized. Okay, we have the basal cover. So based on the cover, based on the base here, so this is one that we determine as one the coverage of the plants, which is the area where the plant intersects the ground. So this is a basal cover. Another one is aerial cover. Aerial cover uh, is the vegetation covering the ground surface above the ground surface. So this is from one end to the end. So they cover, although they is not touching the ground for this tip. So this one they call it as a is also they, consider we consider as the coverage plant. So which is this is the sometimes we call it as canopy. You can visualize, of course, you can visualize aerial cover by considering this as a bird eye view, okay, of the vegetation. So bird eye view of the vegetation. So I use a lot. I use drone a lot to do try to look at the plant cover, okay. So you can most easily measure the cover for method plants that we discussed previously, and shrub species with a well-defined canopy. But cover measurements are applicable for nearly all types of plants. Okay. Of course, cover measurement often used for grasses because of the difficulty in counting grass plants or tillers. Cover is one of the most common measures of community composition because it equalizes the contribution of species that are very small but abundant and species that are very large but few. Okay, of the three measures, density, frequency, and cover, cover is the most directly related to biomass. So a key advantage of cover as a vegetation measure is that it does not require the identification of the individual, of course, as a density does, yet it is an easily visualized and intuitive measures, unlike the frequency. Okay. A disadvantage of cover measures, especially for the canopy cover, is that they can change dramatically over the course of growing season. While both frequency and density measures are fairly stable after germination is complete, the change in cover, okay, over the course of the growing seasons may make it hard to compare results from different portions of large areas where sampling takes several weeks or a few months. Let's say I'm doing try to look at coverage of the rice. Rice only take around 100 days from seedlings to from the seeds to the harvest. So which means that uh, if you want to do the coverage of the bigger plant, you have a very short window. Okay, but it's not only applicable in the short period growth stage, but also in the plants. Because plant keep growing, so the cover, the canopy cover from one season to another probably will different, and which means that you need to very carefully design your experiment or your survey or your monitoring, okay, before you do the measurement for the cover. So of course, sampling design considerations for estimating cover in quadrats are theoretically similar to that of density, where using long, narrow, and fairly large plots will reduce the between quadrat variability and increase the efficiency of the sampling. This design is impractical for most field situations because you cannot accurately and consistently estimate cover in plots with large area, especially long, narrow ones that cannot be completely viewed from one observation point. A better approach is to use smaller quadrats that facilitates accurate over the estimates. So for instance, now I want to develop to look at this plant cover because the drone technology is out there. I must have a drone, and I'm trying to use this drone as part of how to look at the coverage using the uh, from the aerial view. We already have done it using the satellite image, but unfortunately satellite image is not have a accurate period of time. Okay, so that's the problem with the satellite images. But now it's possible. I think within a few years, or to probably next year, the survey using the drone will be will become a mainstream. Okay, so another techniques that have been developed for measuring cover is what we call as line intercepts. Okay, what means by line intercept is canopy is measured along a line intercept by noting the point along the tape where the canopy begins and at the point of which it ends, like this one. Okay, so when these intercepts are added and then divided by the total line length, the result is a percentage cover for that species along the transect. So you can look at this, how the hypothetical calculation that I made here. It's just hypothetical, okay? So line intercept techniques are effective for species with dense canopies, such as shrubs and or matted plants. But line intercepts is more difficult to use for plants with lacy or narrow canopies, such as grasses and some forbs and shrubs, because of the large number of small interceptions that required our evaluation. So of course, and then next is what calls as point intercepts. Cover is measured by point intercept based on the number of hits. Okay, number of hits on the target species out of the total number of points measured. So measuring cover by points is considered the least biased and most objective of the three basic cover measures. Okay, observers need only decide whether the point intercepts the target species. Canopy gaps and cover estimation do not need to be evaluated. So points are measured either with pins that touch the vegetation. Okay, so this here is a hit or miss, or hit or miss, hit, miss, hit, miss. Okay, uh, with a crosshair optical sighting method. Okay, pins have the advantage of being inexpensive and easy to use. So their key disadvantages, however, is the error associated with the diameter of the pin, resulting in overestimation of actual cover, especially for narrow or small leafed species. This is generally not a problem in most monitoring situations where change is of interest rather than the actual cover value. It is important, however, to use the same pin diameter for successive measurement. So don't change the pin that you try to do the point intercepts. So how many points should be placed along each transect? It was best the sample with fewer points and more lines when using the transect as the sampling unit. If you use a transect as a sampling unit, it's better to have a fewer points and more transect lines. This design maximizes the number and interspersion of sampling units throughout the sample area. But if you use point as your sampling unit, okay, using more points and fewer transects may be advantageous. So the largest field expands when points are located along transects is the location and establishment of each transect, maximizing Maximizing the number of points per transect would minimize setup time. So transect may, however, have to be quite long in this design to have points located for far enough apart to be considered independent sampling units. So if the structure of the vegetation presents challenges to establishing long transect, several short transects may actually require less time.